hello, aloha, sawadika, and mabuhay. Good day to all of our students. How are you today? I know that you are very much eager to learn our new lesson. I am your Sir Jeffrey Kadungog of Santa Ana National High School, your teacher broadcaster in Mathematics 10 for Quarter 3 of Week 8. I'm sure that you are all excited, so let's get started. Today, we shall be talking about the probabilities of mutually exclusive events as well as the probabilities of inclusive events, or what we know as the probabilities of non-mutually exclusive events. So are you guys ready? So here are our objectives for today. After going through this discussion for today, you are expected to find the probability of A union B. And second, we are going to illustrate mutually exclusive events. Specifically, you will be able to first find the probability or P of A union B, which is equal to P of A plus P of B, which means the probability of A plus the probability of B. Second of all, we are going to find the probability of A union B, which is equal now to the probability of A plus the probability of B minus the probability of A intersection that of B. And third, we shall be able to solve word problems involving the probabilities of A union B. At the onset of the discussion, let me first tell you what the probability of these events are. So let's define things up. A compound event, when we say compound event, this consists of two or more simple events that are connected by words and or. I know that the simple events have already been discussed in the previous lesson. So, two events are mutually exclusive if both events cannot occur at the same time. Once again, two events are called mutually exclusive if these events cannot occur at the same time. These events have no common elements. So, for us to further understand what these mutually exclusive events I'm talking about, let's go analyze this example. What is the probability that Jose rolls an odd number or a 6? So, for this particular problem, our sample space will be 1, 2, 3, 4, 5, 6. Event 1 will indicate the event of rolling an odd number in a die. So we have the sets consists of 1, 3, and 5. While event 2, on the other hand, is just for rolling a 6. Rolling an odd number or a 6 cannot happen at the same time. Therefore, what kind of event is this? Very good. This is just but an example of mutually exclusive events. So, the probability of union of two mutually exclusive events is found by adding the probability of each event. The illustration here shows the probability of mutually exclusive events. You get to see in the illustration that there are two circles labeled A and B. It says the probability of the union of events A and B is equal to the probability of A plus the probability of B. Or, in other words, we can also say that the probability of events A or B is equal to the probability of A plus the probability of event B. So, let us go now to our example. What is the probability that Jose rolls an odd number or a 6? I have already made mention of our sample space, our event 1, and our event 2. For our solution, the probability of rolling an odd number or a 6 is equal to the probability of rolling an odd number plus the probability of rolling a 6. So this then would now be equal to 3 6 or 3 over 6 plus 1 6 or 1 over 6. Hence, 3 over 6 plus 1 over 6 is equal to 4 over 6. And then, when we reduce this to its lowest term, we can say therefore that the probability of rolling an odd number or a 6 is equal to 2/3. So what then are non-mutually exclusive events? Non-mutually exclusive events, or what we call as the inclusive events, are events that happen at the same time. Hence, the probability of the union of non-mutually exclusive events or inclusive events is also known as the additive rule of probability. Are you familiar with the additive rule of probability? Thus, we add the probabilities of the two events minus the probability that both will occur. It is further illustrated here. Once again, we have two circles, and these two circles overlap, labeled A and B. So for us to further illustrate what non-mutually exclusive events are, we say that the probability of events A, or the union of events A and B, is equal to P of A, the probability of event A, plus P of B, the probability of event B, minus the probability of event A intersection with event B. Or, the probability of events A or B is equal to the probability of A plus the probability of B minus the probability of event A intersection B. So let us proceed with some examples. Example 1. 15 balls numbered 1 to 15 are placed in the basket. A ball is drawn at random. Find the probability that the number on the ball drawn is A, less than 5 or greater than 10. Letter B, an even number or greater than 10. Let us first answer the first question. The probability of drawing less than 5 or greater than 10. First, we will list the numbers less than 5. These are 1, 2, 3, 4. Since there are 4 numbers, then we say that the probability of drawing less than 5 is equal to 4 over 15. Why is it over 15? Because there are 15 balls, if you could remember. Numbers greater than 10 are 11, 12, 13, 14, and 15. You get to see that there are 5 of them. Therefore, we say that the probability of drawing numbers greater than 10 is equal to 5 over 15. Since there are no numbers that are the same in the two events, we say that this particular example is that of a mutually exclusive event. Hence, the solution would be like this. The probability of less than 5 or greater than 10 is equal to 4 over 15 plus 5 over 15. And this is equal to 4 plus 5 equals 9 over 15. And when we reduce that to its lowest term by a factor of 3, the final answer would now be 3/5 or 3 over 5. Fabulous, isn't it? Now let us proceed to question letter B. Here is the solution. The probability of drawing even number or greater than 10. First, we will list the even numbers. These are 2, 4, 6, 8, 10, 12, and 14. So, we see on my hand 7 numbers. So, the probability of getting an even number is equal to 7 over 15. On the other hand, the numbers greater than 10 are 11, 12, 13, 14, and 15. So the probability that you will draw numbers greater than 10 is equal to 5 over 15. Since there are even numbers that are greater than 10, therefore we say that these events is actually what we call as inclusive events or the non-mutually exclusive events. Even numbers that are greater than 10 are 12 and 14, isn't it? So the probability of getting an even number and numbers greater than 10 is equal to 2 over 15. Hence, we say that the probability of getting an even number or greater than 10 is equal to the probability of getting an even number plus the probability of getting a number greater than 10 minus the probability of getting an even number and at the same time it is greater than 10. So in numbers, this is equal to 7 over 15 plus 5 over 15 minus 2 over 15. 7 plus 5 gives us 12 minus 2, therefore we have 10. So that's 10 over 15, which when reduced to lowest terms by a factor of 5, we get the simplified answer to be 2/3 or 2 over 3. Let us now proceed to another example. So for us to fully understand what these mutually exclusive events are in contrast to inclusive events. Think about this particular problem. A card is drawn at random from a standard deck of cards. What is the probability of drawing a queen or a king? I know for a fact that you guys there are very much familiar with playing a standard deck of playing cards. Solution: these two events are mutually exclusive. Why so? Since you cannot draw a card that is both a king and a queen, isn't it? Thus, simply add the probabilities of two events. So, the probability of getting a queen or a king is equal to the probability of getting a queen plus the probability of getting a king. The probability of getting a queen is equal to 4 over 52 because there are 4 queens in a standard deck of playing cards. Also, we have 4 kings in a standard deck of playing cards. So 4 over 52 plus 4 over 52 gives us 8 over 52, which when reduced to its lowest term by a factor of 4 gives us 2 over 13. Therefore, the probability of drawing a queen or a king in a standard deck of playing cards is equal to 2 over 13. What about in this particular problem? A card is drawn at random from a deck of cards. What is the probability of drawing a red ace or a heart jack? These two events are said to be mutually exclusive. Why so? Since you cannot draw a card that is both an ace and a jack, right? So, the probability of getting a red ace or heart jack is equal to the probability of getting a red ace plus the probability of getting a heart jack. So, the probability of getting a red ace is equal to 2 over 52. Why so? Because there are 2 red aces. That of a heart and that of a diamond. So, it's 2 over 52. Plus, the probability of getting a heart jack is only 1 over 52, which is self-explanatory. So 2 over 52 plus 1 over 52 is equal to 3 over 52. this number or this fraction can no longer be reduced to its lowest term. So we say therefore that the probability of drawing a red ace or a heart jack for that matter is equal to 3/52. What about this particular problem? The probabilities of 3 contestants, A, B, and C, of winning the grand prize are 1/5, 1/6, and 1/3 respectively. The probabilities are already given in this particular problem. Assuming that only one contestant can win the grand prize, find the probability that neither A nor C wins. Remember that the question being asked is the probability that neither A nor C wins. But there isn't any mention about the probabilities of the neither A nor C. What is given to us is the probabilities that they are going to win. Since only one contestant can win, the events are said to be mutually exclusive. So, our solution would now be the probability that A or C wins is equal to the probability that A wins plus the probability that C wins. The probability of A that it's going to win is 1/5, while the probability that C wins is 1/3. Adding the two employs the least common denominator or LCD, which is 15. And you can see from our solution that 1/5 plus 1/3 now becomes 3/15 plus 5/15. And that gives us 8/15. 8/15 then is the probability that either A or C wins. But that is not yet the answer to this problem. What we're going to do is that we're going to subtract this 8/15 from 1 because we are going to answer the probability that neither A nor C wins. The probability that is either contestant A or contestant C will win is 8/15. However, the question asks the probability that neither of the two contestants will win. That is, the probability that neither A nor C wins is equal to 1 minus the probability that A or C wins. Therefore, continuing with the solution, we have 1 minus 8/15, which we have previously solved. 1 can be written as 15/15 minus 8/15. So 15 minus 8 gives us 7/15. So 7/15 then is the probability that neither A nor C wins. Let us continue the vigor that you have in learning as we go about this next problem. In a room of 20 people, there are 12 women and 8 men. 6 women and 5 men are wearing red. What is the probability of randomly picking one person who is either wearing red or a woman? The solution would be, in the event of choosing a person who is either wearing a red or a woman shows an inclusive event because there can be a woman who is actually wearing red. So let us start by listing the probabilities of each event. There are 6 women wearing red. So the probability of a woman wearing red is equal to 6/20. There are 11 people wearing red. So the probability of wearing red is equal to 11/20. There are 12 women in the room. So the probability of women is equal to 12/20. So then the probability that the one picked wears red or is a woman is equal to the probability that the one picked wears red plus the probability that it is a woman minus the probability that it is a woman wearing red. Hence, in fractions or in numbers, this is equal to 11 over 20 plus 12 over 20 minus 6 over 20. 11 plus 12 gives us 23 minus 6, that would be 17 over 20. Hence, the probability of choosing a woman or a person wearing red is 17 over 20, regardless of what this woman can be, a natural-born woman or a transgender woman. Let us now then proceed to this next example. In a math class of 30 students, 17 are boys and 13 are girls. On a unit test, 4 boys and 5 girls made an A grade. If a student is chosen at random from the class, what is the probability of choosing a girl or an A student? Ever wonder what kind of probability would this be? Will it be a mutually exclusive event or the probability of an inclusive event? You got it right. The probability of choosing a girl or an A student shows an inclusive event. Let us start with listing all the probabilities. There are 13 girls in a math class of 30, which means that the probability of getting a girl is equal to 13 over 30. There are 9 students with an A grade, which means that the probability of choosing that somebody with an A grade is equal to 9 over 30. There are 5 girls with an A grade. This means that the probability that the one picked is a girl with an A grade is equal to 5 over 30. Therefore, our solution would now be the probability of picking a girl or an A grade is equal to the probability of getting a girl plus the probability that the one picked has an A grade minus the probability that it is a girl with an A grade. In numbers or in fraction, this would be 13 over 30 plus 9 over 30 minus 5 over 30. 13 plus 9 gives us 22, and 22 minus 5 gives us 17. Therefore, the probability of getting a girl or that somebody has an A grade is equal to 17 over 30. You might be feeling a little exhausted right now, but I'm sure that it cannot withstand the vigor that you want to pursue your learning in mathematics. So let's answer the following questions. A box contains 3 red playing cards numbered 1 to 3. The box also contains 5 black playing cards numbered 1 to 5. You randomly pick a playing card. What is the probability that it is black or has an odd number? Is it A, 1/8, B, 3/8, C, 5/8, or D, 7/8? What is your answer? Let us see if your answer is the same with mine. For this particular problem, we first say or establish that it is an example of an inclusive event or a non-mutually exclusive event. Hence, we shall be utilizing the formula, the probability of getting an A or B is equal to the probability of getting an A plus the probability of getting a B minus the probability of getting an A and B. In our problem, it can be translated as the probability of getting a black or odd is equal to 5 over 8, which is derived from the black ones, another 5 over 8, which is derived from the odd ones, which can be found both in red and in black. Numbers 1, 3 for red and numbers 1, 3, and 5 for black. And of course, minus 3 over 8, all of which can be found in the black because these are the odd numbers found in the black ones, 1, 3, and 5. So 5 plus 5 gives us a 10 minus 3, which is equal to 7. Therefore, the answer to this problem is 7 over 8. Letter D. Brilliant. Next problem. You roll a fair six-sided die. What is the probability that the die shows an odd even number or a number greater than 3? So, is it letter A, 2/3, B, 1/3, C, 1/6, or D, 5/6? What is your answer? Let us see. The solution to this problem is that we first establish that once again, this is an example of an inclusive event or a non-mutually exclusive event. So, the probability of getting an even or greater than 3 is equal to the probability of getting an even plus the probability of getting a number greater than 3 minus the probability that it is an even number and it is greater than 3. So in numbers or in fractions, this is equal to 3 over 6 plus 3 over 6 minus 2 over 6. Because there are 3 even numbers and there are also 3 numbers greater than 3. And what is that 2 over 6? Where does that come from? 2 there represents those even numbers greater than 3. So 3 plus 3 is equal to 6 minus 2 equals 4 over 6, which when reduced to its lowest term by a factor of 2, the answer would now be 2/3. Very good. What about this next problem? A magazine contains 14 pages. You open a random page. What is the probability that the page number is 3 or 7? Is it A, 1 over 14, B, 3 over 14, C, 1, 7, or D, 2, 7? What would now then your answer be? Let us see. For this particular problem, it is no longer an inclusive or a non-mutually exclusive event, but this is exhibiting that of a mutually exclusive event. Why so? Because you cannot have a number 3 or a number 7 all at the same time. So then the formula to be used is simply the probability of A or B is equal to the probability of getting an A or the probability of getting a B. In our problem, for example, we say therefore that the probability of getting a 3 or 7 is equal to the probability of getting a 3 plus the probability of getting a 7. The probability of getting a 3 is 1 over 14, while the probability of getting a 7 is also 1 over 14, which when added together becomes 2 over 14, and when reduced to lowest term by a factor of 2, we now have 1 over 7. Therefore, 1 over 7 is the probability that the page number is 3 or 7. Now let us try to determine if each pair of events are mutually exclusive, ME, or inclusive, letter I. We are going to say it's ME for mutually exclusive or I for inclusive. This is the first scenario. Drawing a diamond or a black card from a standard deck of cards. Is it ME or I? ME does not mean mechanical engineer here, or I doesn't mean industrious. ME again stands for mutually exclusive. I, on the other hand, stands for inclusive. So, for drawing a diamond or a black card from a standard deck of cards, this is an example of a mutually exclusive event for a very obvious reason that you do not have a diamond which is black in a standard deck of cards. Right? So, let's move on to another scenario or another example, which is drawing a king or an ace from a standard deck of cards. Would that be ME or would that be an I? Your guess is as good as mine. Very good. That's ME or mutually exclusive. Once again, because a king is definitely different from that of an ace in a standard deck of cards. So you cannot have them both all together. Now, the next thing is drawing a 5 or a 6 from a standard deck of cards. Is it ME or I? Brilliant. It is still ME, mutually exclusive, because 5 is 5 and 6 is 6. These are two different numbers, right? Unless you prove otherwise, that these two numbers are just but the same. But in reality, so far, it isn't. The next thing that we have to analyze whether if it's ME or I is when you are attending a class in school and you are sleeping. You are attending a class in school and you are sleeping. Will it be an ME? Will it be an I? Mutually exclusive or inclusive event? And your honest answer should be an inclusive event. That's right, because whether we like it or not, admittedly, there are really students who are sleeping in the class while they are attending it. Right? Who among you here are like those students I have made mention of? Don't worry, guys. I am one of those when I was a student. Okay. And the last question, not really a question, but a scenario that I would like you to ponder whether it is ME or I, is that when you roll a fair die and getting an even number or a multiple of 6. Rolling a fair die and getting an even number or a multiple of 6. Is that an ME or an I? The answer is, voila, it's inclusive. Inclusive because we can actually get a multiple of 6, which is actually 6 itself when we roll a fair die, isn't it? After all that we have been discussing all this time about mutually exclusive and non-mutually exclusive events, I think it is high time for us to have a gist of the discussion for today. Let us remember the following. First, the probability is a term that refers to the likelihood of an event or for it to happen or to occur. Second, mutually exclusive events are events that cannot happen simultaneously. Third, the formula in finding the probability of mutually exclusive events is the probability of A union B is equal to the probability of A plus the probability of B. Fourth, non-mutually exclusive events or inclusive events are events that can happen at the same time. So the formulas in finding the probability of non-mutually exclusive events or inclusive event is P of A union B is equal to P of A plus P of B minus P of A intersection B. There are also things that you should be reminded of. When the particular problem is mutually exclusive, you only have to remember one particular operation, and that is addition. On the other hand, if you say that the event is non-mutually exclusive or inclusive events, then you get to remember both addition and subtraction in the formula. Now, after a series of identifying events to be either ME, mutually exclusive, or I, inclusive, ME or I, this is a question I'd like you to answer now. Who do you think is more beautiful, me or I? You're not given a choice here. You'd rather either say me or I. So that's just kidding. So thank you very much for painstakingly listening to our discussion all throughout the day. This has been Sir Jeffrey Kadungog of Santa Ana National High School, and I am your teacher broadcaster in Mathematics 10. Always remember, stay at home and let's continue the fight for life amidst this pandemic.